Here's the classic example of a block on a ramp. So we have a block of mass m, and it's on a ramp with no friction. So we know that eventually the block is going to accelerate down the ramp. Okay, so how can we figure out what that acceleration is? We need to figure out the net force on the block, which must end up pointing in the same direction as the acceleration. So in this case, it kind of helps to visualize if we draw the free body diagram on the picture of the block itself. So if we start here, first of all, we're going to have a force of gravity, which I will draw nice and large, and we'll see why in a second. And then we're also going to have a normal force, and the normal force points normal or perpendicular to the ramp. So in this case, it doesn't point straight up, it points at an angle like this. Okay, so we can see right now that that these forces have components in multiple directions. So you might say, well, let's draw our usual x and y axes, right, in the horizontal and vertical directions, and break the normal force into components. However, in this case, that's not going to be a useful choice of axes. And the reason for that is that if we make our usual choice of axes, like so, then the acceleration is not purely in the x or y directions. So that's going to result in, we're going to have to find two different components for the acceleration and then put them back together again. So rather than do that, let's not use those axes that we are familiar with and align one of our axes with the acceleration. So that means that we're going to have our positive x-axis parallel to the ramp and our positive y-axis vertical to the ramp. Now that shows that our normal force is already parallel to the y-axis, so it's actually going to be the force of gravity that gets broken into components in this case. So let me draw sort of a y-axis here in dotted lines. And that means that we're going to have a component of gravity that points in the x direction. So let me draw that here, F sub g x. And then we're also going to have a component of gravity that points in the y direction, F sub g y. Okay, so this angle right here is the 90-degree angle in our right triangle that I've just formed. So the F sub g, that's the hypotenuse. And so we'll use this angle here as the angle that we're going to use to break down that force into components. Now the question is, what is that angle? So we want to figure out what that angle is. And if we look at this angle right here, that's 90 degrees, right? The angle between the y-axis and the ramp is 90 degrees because that's how we defined our axes. So that means that this angle, which we'll call alpha over here, and this angle plus called beta, they add up to 90 degrees. So that's alpha plus beta is equal to 90 degrees. Okay, and then we can also look at this triangle over here with theta on one corner and alpha here, and then this angle is also going to be 90 degrees. Now we know that the angle of a triangle add up to 180, so I can say alpha plus theta plus 90 degrees equals 180. Okay, or if I subtract 90 from both sides, that's alpha plus theta is equal to 90 degrees. So if alpha plus beta and alpha plus theta both equal 90 degrees, that means that theta and beta are the same. So that means our angle beta is the angle of the ramp theta. Okay, so we can just go ahead and use that. Okay, so now that we've got that kind of sorted out, okay, so you know, that argument about what this angle is, we have to do it once, and now we know it, and so we're good to go. So that angle is theta. And as we do that, that's going to allow us to break the force of gravity into its x and y components. Okay, so looking at that picture, we can say then that in this case, f sub g y is adjacent to the angle theta, right? It's touching it. So that means f sub g y is going to be equal to fg cosine theta, and f sub g x is equal to fg sine theta. Right, so that's different from the case in projectile motion where the angle was made with the horizontal. Here the angle is made from the vertical, so the y component goes with cosine. Okay, so if all we want to know, we can now use Newton's second law, right? And if we want to look at the x direction, right, we can say f net in the x direction. Which components go into that? Well, it's just f sub g x. There's nothing else in the x direction. The normal force does not have a component in that direction, and there's no other forces. So that's going to be equal to ma. Right? We already knew that the acceleration would be in the direction parallel to the ramp, right? And that's fg times the sine of theta is equal to ma. Now we also know that the force of gravity is the mass of the object times the acceleration due to gravity, so that gives us mg sine theta is equal to ma. And since there's a mass on both sides of the equation, I can divide both sides by mass, and the mass cancels out. So that tells me that the acceleration of a block on a frictionless ramp is equal to g times the sine of that angle. of the ramp. And so the mass of the block does not affect the acceleration, which is interesting. Now, we're kind of used to that already in the case of free fall. When the only force is gravity, all objects have the same acceleration. So kind of makes sense because here, the main thing affecting it is gravity. We can also check this out to make sure that it makes sense. If I say, well, what happens if the angle is 0? If theta equals 0 degrees, sine of 0 degrees is equal to 0, so that means the acceleration is 0. Well, what's a ramp with a 0 angle? It's just a table, right? So a block sitting on a table does not accelerate. And we can also look at if theta is equal to 90 degrees, then the sine of 90 degrees is equal to 1. So in that case, the acceleration is equal to g. Well, what's a block, or what's a ramp with an angle of 90 degrees? It's just a wall. So if you drop a block next to a wall with no friction, the acceleration is going to be g because it's in free fall. Now, for completeness, we should so that's a good check, right? The fact that we that we have these cases where we know what the answer should be, we should check that our new equation matches those. Now, we also have the case of, or the other direction, F net y. And so we can look at our free body diagram and say, what are the forces in the y direction? Well, in the positive y direction, we have the normal force, and in the negative y direction, we have FGY. And what does that equal to? It's mass times acceleration in the y direction, but that's 0. Right, so what that tells me is that the normal force is equal to the y component of gravity, which I could go ahead and write is mg cosine theta is the normal force. Now, why would I care? The example that I always give is, if you were to go skateboarding down a ramp, but put a scale on the skateboard, and you wanted to know what the scale would read, well, that would be a normal force. Right? It's not going to be your entire weight because it's just going to be a component of it. So that's not particularly realistic, but in the future, we'll see that we need to know this normal force in the case that we're dealing with friction. So it's a good habit to always analyze Newton's second law in both x and y directions and see what information you can glean from those.
In the case of science, you think that one of the things that make it very difficult is it takes a lot of imagination. It's very hard to imagine all the crazy things that things really are like.